Hello everyone, in this project I worked on the home credit default risk classification task. The goal was to predict whether a loan applicant would default on repayment. For this final hackathon, I did not focus only on predictive performance. I approached the project from a responsible AI perspective, so my goal was to build a model that is not only effective but also fair, interpretable, and accountable. I start with the main application table, which contains demographic, financial, and behavior information about the applicant in the notebook. I first reviewed the structure of the data, missing values, feature type, and the class imbalance. One important finding was that the dataset is highly imbalanced because the default class is much smaller than the non-default class. Because of that, I did not rely on accuracy alone. I used the ROC AUC as my main evaluation metric, and I also report precision, recall F1 score, and the confusion metrics based the result to better understand model performance. For pre-processing, I handled missing values separately for numeric and category variables, encoded category code features, and scaled numerical features where appropriately. I also removed SKIDs CURR from the modeling features because it is only identifier and should not be used as predictive variables. Then I used a stratified holdout split to create training and validation sets, which served as my main performance validation approach. I trained and compiled three models: logistic regression as a baseline, random forest, and XGBoost. This gave me both a simple baseline and stronger ensemble models. Among them, XGBoost produced the best overall balance of ROC, AUC, recall, and F1 score, so I selected it as the final model. I also evaluated without using the confusion matrix and considered the meaning of tree positive, tree negative, and false positive and false negatives. In this landing setting, these arrows matter differently. A false or positive mean predicting default for someone who would actually repay, which could unfairly deny access to credit. A false negative means approving someone who later default, which creates risk for the lender. So one important point in my analysis was the model errors are not natural. After selecting the final model, I focused on explainability. I used feature importance and SHAP analysis to make the model more transparent. At the global level, SHAP helped identify the most influential features across the four datasets. At the local level, it helped explain an individual prediction by showing what variables pushed a special applicant's scores higher or lower. This is important in credit risk modeling because explanatory supports accountability. If a model influences a lending decision, we would be able to explain why that prediction was made. A major part of the notebook was fairness and analysis. I evaluated the model across both gender and age groups. I first compiled subgroup performance, and then I calculated formal fairness metrics, including demographic parties differences, demographic party ratio, equal opportunity difference, false positive rate gap, false negative rate gap, and the equalized out gap. For gender, results showed that the model didn't behave equally across male and female applicants. Male applicants had a higher predicted positive rate, and the fairness gap were clearly non-zero for age. I also found meaningful differences across groups, especially between younger and older applicants. At the same time, I noted that the oldest group in the validation set was relatively small, so those results should be interpreted carefully. To go beyond only identifying disparities, I also performed a sensitive features ablation test. In the experiment, I retrained the final XGBoost model after removing cogender and disperse. This allowed me to test whether those direct demographic features were contributing to the fairness gaps. The results were important. After removing those features, our CUC remained both stable and even improved slightly, which means the rankability of the model was preserved. However, some threshold-based metrics, including accuracy, precision, recall and the F1 score, become weaker. At the same time, several gender fairness metrics improved. In other words, removing direct sensitive attribute improved fairness while keeping overall ranking quality stable. Although it reduced some classification performance, I think this was one of the most meaningful findings in the notebook because it showed a real trade-off between fairness and operational performance. I also included threshold turning analysis. Instead of assuming that 0.5 must be the correct classification threshold, I tested several thresholds and compared precision, recall, F1 score, false positive rate, and false negative rate. In my validation sample, 0.5 also turned out to be the best threshold by F1 score. Even though the threshold didn't change, this analysis was still useful because it showed that I validate threshold rather than accepting it automatically. From an ethic perspective, the measure shows why credit risk precision is a high-stake machine learning problem. A model can have strong overall performance and still resist fairness concerns. Historical lending data and reflect existing bases, and even if direct sensitive features are removed, cross variables may still carry demographic information. That's why predictive performance alone is not enough. Ethical analysis requires looking at who may be helped or harmed by model decision and whether those harm and distribute fairly. Finally, I discussed production readiness. My conclusion is that this notebook is a strong, responsible AI prototype, but not a fully autonomous production system. A real deployment would require data quality checks, scale validation, draft monitoring, fairness monitoring over time, threshold review documentation, and human oversight for high impact or borderline cases. In other words, the model should support decision making, not replace the governances. So, to conclusion, my final model was XGBoost because it provided the best overall predictive performance. I improved interpretability using feature importance and SHAP, and I evaluated fairness using formal responsible AI metric across gender and age. The abolition tests showed that removing direct sensitive features improved fairness while keeping ROC and UC board stable, which highlights an important trade-off between fairness and classification performance. Overall, my final recommendation is to use the model as a decision support tool in lending, not as an overgoverned automated approve or rejection system. Thank you.